Have you ever wondered where everything came from? I'm talking about everything, the stars, the planets, even you and me. The answer, my friends, lies in an event so monumental, so mind-bogglingly awesome, that it's simply called the Big Bang. Picture this, about 13.8 billion years ago there was nothing. Not empty space, not darkness, just nothing. Then, in a fraction of a second, a tiny point, smaller than an atom, exploded with unimaginable force. This wasn't your typical explosion, like fireworks on the 4th of July. This was the mother of all explosions, the birth of our universe. From that tiny point, space itself expanded rapidly. It's still expanding today, like a balloon being inflated. As the universe expanded, it cooled, and energy transformed into matter, the very building blocks of everything we see around us. This, my friends, is the essence of the Big Bang theory. The idea that our universe originated from a single point and has been expanding and evolving ever since. So buckle up, because we're about to embark on an incredible journey to explore the mysteries of the Big Bang. Okay, so we've talked about this tiny point that exploded. But how tiny are we talking? Imagine all the matter in the universe, all the stars, planets, galaxies, squeezed into a space smaller than a grain of sand. That's how incredibly dense and hot the universe was at the very beginning. This state of extreme density and temperature is what scientists call a singularity. Think of it like the ultimate cosmic pressure cooker, where the laws of physics as we know them break down. It's impossible to even fathom the conditions inside the singularity, because it's unlike anything we've ever experienced. But here's the amazing part. As the universe expanded from this singularity, it began to cool down. And as it cooled, something incredible happened. Energy started to transform into matter. Remember Einstein's famous equation, E equals mc squared? It tells us that energy and matter are two sides of the same coin, and they can transform into each other. This transformation of energy into matter is what gave birth to the first elementary particles, the building blocks of everything in the universe. It's like the universe went from a formless, chaotic soup of energy to a more organized state with the emergence of these particles. In the first few moments after the Big Bang, the universe was a chaotic and unbelievably hot place. We're talking trillions of degrees Celsius, hotter than the core of any star. At these temperatures, matter couldn't exist as we know it. Instead, the universe was filled with a sea of elementary particles like quarks, leptons, and bosons, constantly colliding and interacting. As the universe continued to expand and cool, these particles began to combine and form more familiar particles like protons and neutrons. Imagine a dance floor filled with people moving frantically. As the music slows down, some dancers pair up, forming a different kind of dance. That's kind of what happened with these particles. This period is called the particle era, and it lasted for about the first second after the Big Bang. By the end of this era, the universe had cooled down enough for protons and neutrons to start sticking together, forming the first atomic nuclei, the hearts of atoms. This process is called nucleosynthesis, and it's a crucial step in the formation of the elements that make up everything we see around us. It's like the universe was setting the stage for the creation of stars, galaxies, and even life itself. For hundreds of thousands of years after the Big Bang, the universe was still a pretty boring place. It was basically a giant expanding cloud of hydrogen and helium gas, with tiny specks of other elements sprinkled throughout. But even in this seemingly dull cosmic soup, something incredible was brewing. The first stars were about to be born. Gravity, the force that makes things fall to the ground here on Earth, was also at work on a cosmic scale. Over vast stretches of time, gravity pulled together clumps of hydrogen and helium gas, making them denser and hotter. As these clumps grew larger, their gravity intensified, pulling in even more gas. Eventually, the pressure and temperature at the center of these giant gas clouds became so intense that nuclear fusion began. This is the process where hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy in the process. Boom! The first stars ignited, bathing the universe in their brilliant light. These first stars were massive, hot, and short-lived, but they played a crucial role in the evolution of the universe. They forged heavier elements in their cores, elements like carbon, oxygen, and iron, which are essential for forming planets and even life as we know it. Section 5. The universe is expanding like a balloon blowing up. Remember that balloon analogy we talked about earlier? Well, it turns out the universe is not only expanding, but its expansion is also accelerating. That's like blowing into a balloon and watching it expand faster and faster. This discovery, made in the late 1990s, came as a complete surprise to astronomers. They expected the expansion of the universe to be slowing down due to the gravitational pull of all the matter it contains. But instead, something seems to be pushing everything apart at an ever-increasing rate. Scientists call this mysterious force dark energy, and it's one of the biggest unsolved mysteries in astrophysics today. We don't know what dark energy is or where it comes from, but we know it's out there, and it's profoundly affecting the fate of the universe. Some scientists believe that dark energy will continue to drive the expansion of the universe forever, eventually leading to a big freeze, where everything is so far apart that the universe becomes cold, dark, and empty. Others speculate that dark energy might change over time, potentially leading to other cosmic scenarios like a big rip or even a big crunch. Section 6. Before the Bang, the ultimate mystery. The Big Bang Theory does an amazing job of explaining how our universe evolved from a tiny point to the vast cosmos we see today. But it leaves us with one huge mind-bending question. What came before the Big Bang? This is where things get really tricky, because the Big Bang represents the very beginning of time and space as we understand them. Asking what came before is like asking what's north of the North Pole. It's a question that might not even have an answer within the framework of our current understanding of physics. Some physicists believe that the Big Bang wasn't actually the beginning of everything, but rather a transition from a previous state of existence. They propose ideas like a cyclical universe where big bangs and big crunches happen repeatedly, or a multiverse where our universe is just one of many bubbles in a much larger cosmic foam. However, these ideas remain highly speculative, and we lack the observational evidence to confirm or refute them. The mystery of what, if anything, came before the Big Bang might forever remain one of the biggest enigmas in science. Section 7. Echoes of the Big Bang proof in the cosmic afterglow. The Big Bang theory isn't just a cool story, it's supported by a mountain of evidence. One of the most compelling pieces of evidence is something called the cosmic microwave background radiation, or CMB for short. Imagine the Big Bang as a massive explosion. You'd expect some heat left over from that explosion, right? Well, the CMB is exactly that. It's a faint afterglow of radiation that permeates the entire universe. This radiation was discovered by accident in 1964, and it provided the first direct observational evidence for the Big Bang. The CMB is like a baby picture of the universe, showing us what it looked like just 380,000 years after the Big Bang. Another key piece of evidence is the expansion of the universe itself. By observing distant galaxies, astronomers have found that they are all moving away from us, and the farther away a galaxy is, the faster it's receding. This observation strongly supports the idea that the universe is expanding from a single point, as predicted by the Big Bang theory. Finally, the Big Bang theory also accurately predicts the abundance of light elements in the universe, such as hydrogen, helium, and lithium. These elements were formed in the first few minutes after the Big Bang, and their observed abundances match the predictions of the theory with remarkable precision. Section 8. Why the Big Bang matters, our cosmic story unveiled. So, why should we care about something that happened billions of years ago? Well, the Big Bang isn't just about distant galaxies and abstract physics, it's about us. It's the story of our cosmic origins, the grand narrative that connects us to the vast universe we inhabit. Understanding the Big Bang helps us answer some of the most fundamental questions humans have ever asked. Where did we come from? How did the universe begin? Are we alone in the cosmos? By studying the Big Bang, we're essentially piecing together the history of our existence, tracing our lineage back to the very first moments of creation. Moreover, the Big Bang has profound implications for our understanding of physics and the nature of reality itself. It forces us to confront the limits of our knowledge and to develop new theories that can explain the extreme conditions of the early universe. The pursuit of these answers has driven some of the most exciting and groundbreaking discoveries in science, and it continues to inspire new generations of scientists to explore the mysteries of the cosmos. Section 9, the future of the universe, a never-ending story. The Big Bang gave our universe its explosive beginning, but what about its end? Will it be a grand finale, a slow fade, or something in between? The fate of the universe depends on dark energy. We might face a big freeze, galaxies drifting apart, or a big crunch, collapsing back to a singularity. The ending is far from written. Studying the Big Bang will captivate us for generations. The Big Bang holds the key to cosmic secrets.